Assalamualaikum and good afternoon. Today we will discuss about tutorial of open channel, but we are focusing on the hydraulic jump. Might be a few equation is not discussed in the theoretical part, so I hope you could give your attention to this tutorial and please jot down the important equation that you need to use to solve the hydraulic jump problem. So as I said, in open channel, it not just a flow of liquid in a conduit, in a open conduit, but one of the major problem, the major point in open channel flow is to solve hydraulic jump problem. So as you know, previously, we described the hydraulic jump as a flow like this, and then because the energy is very high, and then suddenly the depth of the flow will increase. So this is the symbol of hydraulic jump. Okay, so let's say we have example 6 here. Consider the flow under the slice gate if y1 equal to 10 feet. And all losses are neglected except the dissipation in the jump. Calculate y2 and y3 and the percentage of dissipation. So in this tutorial, we will look how to calculate or how to predict the y2 and y3 before and after the hydraulic jump. So why we bring you this kind of question? Because the hydraulic jump here is actually the losses, the major losses in open channel. When hydraulic jump occur, they will they will absorb a lot of energy. Then the energy between the before and after here will have different. So that's why in this question they ask to calculate the percentage of dissipation of energy here. Okay, let's say we have this situation, a slice gate here. So the water level here is 10 feet. And then when we use feet here means we are using the British unit, okay? The English unit, so means please be careful in terms of the amount of gravity. So for British, we use 32.2 feet over second square later on. Okay, let's say we have this situation. So we have a slice gate here, the water flow. Okay, and then because it's start from a very high location at 10 feet here. So and then the Froude number increase, then the hydraulic jump occur. And we need to predict what is the water depth here and the water depth at the end after the hydraulic jump here. Okay, so first we calculate the energy. So as you know, we have a 0.1 here at the inlet, 0.2 before the hydraulic jump, and 0.3 after the hydraulic jump. So for 0.1 and 0.2 here, there are no hydraulic jump. So we could say that the energy at 0.1 is equal to energy at 0.2. So we could write as this one. So, and then we write down the energy equation. So I think you could write down like this. So the equation is totally similar with Bernoulli equation. In Bernoulli, we have P over rho G plus V square over 2G plus Z. So because the pressure is atmospheric pressure, so we don't have any terms in of pressure. So we have V square over 2G and Z. But here in our syllabus, we will replace the word the alphabet Z with Y, Y1, Y2, Y3, and so on. So we have the energy at 0.1 and 0.2 is equal. So we could write like this one, and then we substitute with all the parameters that we get. So we have Y1 is 10 feet, and then the velocity is mentioned as 2 feet per second. So we substitute the 2 here, and then please be careful if you are using British unit, the gravity acceleration is 32.2 feet per second square. So, and then we don't have any information for point number 2. So we leave it blank here, and then we name this term as equation number 1. So, and then if you see this equation, we found that we have two unknown parameters. One is y and another one is v. So means that we need to create another equation to make sure that we could solve this problem simultaneously. So we use energy equation here. Then we could use the continuity equation to create another equation. We know that the flow rate is constant, so we could say that Q1 is equal to Q2, and it is also equal to A1 V1 equal A2 V2. So because we assume that the width is constant, or you just imagine like this, because we have this idea, we imagine that all the width here is actually the same value. So means that if you use the equation here, we could cancel off the value of width. So and then we could write the equation as y1 v1 equal y2 v2. We substitute the value 10 for y1 and 2 for v1, and then it's still unknown for y2 v2. So and then we could rearrange this calculation become v2 is equal 20 over y2. So we name this as equation number 2. So you could see that now we have equation 1, and then we have equation 2 here, so we could do the simultaneous solution. So after we do the simultaneous solution, we could solve it. Then we could get the value of this one. Also, might be it's not straightforward, but again, if you learn how to use your scientific calculator, actually you could solve this problem easily in your scientific calculator. So if you use that, you will find that the y2 is equal 0.82 feet. Then the velocity is 24.4 feet per second. So again, here I hope you could self-check your answer. Okay, you know that the height is 10 feet, so here it must be less than 10 feet. So might be the answer showing here 0.820 feet is reasonable. Sometimes because we solve y square here, so maybe you could get two value. So please make sure that you will take the correct one. So by solving this one, we know that the y2 is 0.82 feet, v2 is 24.4 feet per second. Okay, now we are solving about the energy, or about the situation where it is before and after the hydraulic jump. So the main equation that you should remember is shown in this slide. So you need to remember as 2y2 over y1 is equal 1 plus 8 front number 1 square in bracket square root minus 1. So this is actually the relationship between the energy before and after the hydraulic jump. So please make sure that the numbering is correct. So number 2 here is actually something happened, something in after the hydraulic jump, and the superscript 1 here is actually something that occurred before the hydraulic jump. Okay, let's say we are using this equation. So what we need to do is we need to calculate the float number at point 2. So the equation for float number is v over square root gy. So we substitute the value of v2. So and then we substitute the gravity and also the height of y. So we get the float number is 4.75. So you will find that the float number here is bigger than 1, so means that it has possibility to create hydraulic jump. And then from the image, from the figure, it show you that the hydraulic jump it was occurred. So and then we substitute in this equation. So we found that the y3 is equal 5.11 feet. So and then how we predict the energy of E2. So we could say that the energy of E2 is Y2 plus V2 square over 2G. So we substitute the height of Y2 and then we substitute the velocity for V2, and then we could get that the total energy is 10.06 feet. So and then we calculate the energy at point number 3. So this is the equation for energy at point number 3, Y3 plus V3 square over 2G. So previously we get the value of Y3 here. So we need to calculate the value of V3. So again, please remember this one. If you have hydraulic jump like this, so energy before and energy after hydraulic jump is not the same, but the flow rate, okay, the flow rate is actually the conservation of mass. So the mass before, the Q before and Q after the hydraulic jump, so it's still equal because flow rate is actually reflecting the conservation of mass. So we believe that mass cannot be created. It only can be transformed from one point to another point. So it means that in this situation, we have hydraulic jump. We cannot equalize point before and after the hydraulic jump by using idea of energy. But we could equalize flow rate at point number 1 with the flow rate at point number 3. So if we equalize flow rate 1 and flow rate 3, we substitute all the value, so we could get the velocity at point number 3 will be 3.912 feet. So we substitute into this equation, so we could get that energy at point 3 is 5.348 feet. So you could see this, the energy at point number 3 is lower compared to the energy that we get at point number 2. So if you calculate the energy at point number 1, it will show the same amount as 10.06. But after the hydraulic jump, the energy is reduced to 5.348 feet. So and then, if we make analysis of this one, we found that the energy E3 is 5.348 and energy at point 2 is 10.0.6. So means that the energy losses is 4.712 feet. So and then if we calculate the dissipation of all the reduction of energy, we could get the reduction is 46.8%. So this is the way we calculate the difference of energy before and after the hydraulic jump. So and then in certain textbook, they will give you an equation to calculate the energy loss, so or the HF. So I think you still remember in Fluid Mechanics 1 and Fluid Mechanics 2, we use HF as head of losses, frictional head. So the equation is y3 minus y2 cubed by the power of 3 divided by 4y2 y3. So if we substitute all the value, we will find that the losses is 4.712, same with what we calculate previously here. So this is the idea how to calculate problem in hydraulic jump. So means that you need to remember the energy equation, and then you need to remember the Froude number. You need to remember this equation. Okay. However, the trick is if you have hydraulic jump, the energy before and after is not the same. Okay, so the energy is not the same, but the flow rate is equal before and after the hydraulic jump. So please remember this situation.